Now moving on to our next topic, that is statistical foundation. So we're moving on to descriptive statistics. We have the terms population, sample variables, and distribution metrics like moments, mean, variance, skewness, kurtosis, and spread. So let us go over all these topics in depth. Okay. So descriptive statistics forms the bedrock of the statistical foundation, providing essential tools and terminology required to summarize, visualize, and understand the characteristics of any data set before conducting these advanced inference or modeling. So basically, some data terms. First, we have population, which is defined as the total set of observations representing the whole of all relevant members or observations in a study. Then we have sample. It is a portion of population, typically extracted through random sampling. Then we have observations, which is basically the individual items that are measured or counted during an experiment, often simply referred to as samples. Then we have variables, which are basically the features that we are measuring, which can be classified as numeric, categorical, or factor variables. Then we have random variables. It is a concept inherently linked to its distributions and their visualization. So some methods include histograms like hist-x, density plots using this, and drug plots using this. Now, measures of distribution shapes, moments. The shape of distribution is defined mathematically by the moment. So it's basically we get the total probability, a fundamental moment, then the mean. Let us go through this. Then we have the mean, uh, the key measure of central location. Then we have the variance, which measures the average square distance from the mean. So we have population variance versus sample variance. Okay, let's go through that as well, which is not mentioned here, but we'll go through it in detail. Skewness measures the asymmetry of the distribution around its mean. Kurtosis measures the tailedness of the distribution, indicating how peaked or flat it is relative to a normal curve. And measure of spread and dispersion. So we have quantiles. These are rank statistics used to describe the spread in distributions. We have quantile plots plotted using QQ norm in R, often used alongside tests like Shapiro dot test, which help compare observed data distributions against theoretical distributions. Then we have interquartile range, that is IQR, known as the mid spread or edge spread. This is a rank ordered statistics that focuses on middle 50% of the data. Then we have range found by calculating the distance between the minimum and maximum values. Critically, the source that I've chosen is basically posing a quiz question highlighting the main issue, that is the range is highly susceptible to outliers as a measure of speed. So we have standard deviation, which measures the which is the measure of spread that, like variance, requires distinguishing between population standard deviation and sample standard deviation. And we have box and whisker plots, which are visual tools to graphically display the distribution, summarizing the key spread metrics. Now, some normal distribution characteristics. Basically, we have the 3 sigma rule, 68, 95, 99, which states that approximately 68% of the data falls within one standard deviation of the mean, 95% of the data falls within two standard deviations, and 99.7% within three standard deviations. Then we have central limit theorem, which is a fundamental concept because it applies to any distribution. It asserts that given a large enough sample size, the distribution of the mean is approximately normal, regardless of the form of the population distribution. Right. So that's about it. Now, moving on, we've done this, and statistical inference, as you can see, we have done all these things. Let us go through statistical inference. So that's the question that is popping up in my head. So let's discuss what the sources say about statistical inference in larger context of statistical foundation. Right. So we'll be discussing that. All right. So we have hypothesis testing, which involves formal statistical tests designed to assess evidence regarding a claim about a population parameter or relationship between variables, like t-test, ANOVA, analysis of variance, and Wilcoxon rank sum test. Then we have parameter estimation, which involves using sample data to estimate unknown population parameters, like simple linear models and generalized linear models. Now, what is the role of normal distribution? It basically is explicitly used as an example in inference. Distribution of data is crucial for determining which hypothesis test or parameter estimation method is appropriate. The CLT, that is central limit theorem, guarantees that given a large enough sample size, the distribution of the mean is approximately normal, regardless of the form of population distribution. Then we have Bayesian inference, which is basically a framework for calculating posterior probability, the disease given symptoms of a hypothesis theta s given data x. So it exploits real world asymmetry in information. The process involves combining the prior probability p theta of s, which is the background frequency of the disease, with the likelihood px given theta s, which is the probability of the symptom given the disease. This is probability of the disease given the symptom, and this is probability of the symptom given the disease likelihood. Via the Bayes rule we calculated. Then we have maximum maximum a posteriori estimate, which is a form of Bayesian inference that maximizes the posterior probability utilizing full Bayes rule formula. Right. Now moving on, association, causality, and confounding. So a crucial aspect of statistical inference is correctly interpreting relationships and avoiding common pitfalls when drawing conclusions. So association versus causation. So basically, correlation is not causation. While inference methods can establish association using tools like covariance and correlation, determining causation requires more rigorous modeling, which is addressed through fields like causal inference. So we have confounding factors. Real world statistical analysis must account for confounding. A confounding factor, like age, influencing both shoe size and IQ, right? A folk structure in a Bayesian context can create an apparent correlation that does not represent a direct causal link. Recognizing hidden confounding factors is essential for accurate inference, right? Now, we basically have this part, and which is not necessary, so we can move on. Now we have causality and correlation. Let us discuss this in depth. So basically, in that we have three subtopics. Correlation is not causation. Challenges in association, which are basically Anscombe's quartet, confounding factors, Simpson's paradox, and always visualize data first, and causal inference, conditional probability, and asymmetry of information. So we'll be discussing that. Let us close this. Okay. So the fundamental distinction between correlation and causation. What is association or correlation? It basically refers to the statistical association between two variables, right? Any two variables, we have association or correlation between them. It can be quantified using the covariance and correlation formulas. Scatter plots can visualize these associations, such as the relationship between wrist and neck circumference or wrist circumference and height. The danger of misinterpretation is drawing causal inferences solely from correlation is hazardous, right? That is why it is saying correlation is not causation. The sources illustrate this using Anscombe's quartet, where four distinct data sets exhibit identical summary statistics, including correlation and simple linear regression results, despite having drastically varied appearances and non-linear relationships when visualized. This highlights the fact that uh, we always need to visualize the data first before relying on summary statistics for interpretation. Secondly, modeling for causality and association. So, data science for medicine employs specific techniques to model both correlation, association, and explicit causal relationships. So, covariance and correlation, these are mathematical tools used for modeling association. Covariance basically measures how two variables change together, and correlation is the standardized measure of this covariance. So, feature selection techniques like correlation based feature selection rely on the concept of correlation to reduce dimensionality. The principle is that a good feature subset contains features highly correlated with the class, that is the outcome, but uncorrelated with each other. Secondly, modeling causality and conditional dependence. So we use Bayes rule and asymmetry. The foundation for modeling directed relationships lies in the concept of conditional probability and asymmetry of information. So Bayes rule exploits real-world asymmetry in information to calculate probability of a hypothesis given the data. So this is the example. Then we have Bayesian networks. So these are explicitly designed to model the world of conditional probabilities and represent uh, relationships with directed arrows suggesting causal or conditional influence. The construction of Bayesian networks is central to learning policy for complex socio-demographic challenges like mitigating the longevity gap. Now, causal structures. So Bayesian networks rely on graphical building blocks that depict conditional relationships. Mediation chain represents a direct sequence like smoking, then arrow tar, then arrow lung cancer. Then folk confounding represents a common cause where a single variable influences two others, like age influences shoe size and IQ. The challenge of confounding, the core difficulty in establishing causality is managing confounding. So, what are confounding factors? These are basically hidden factors that can create spurious correlation. For instance, an observed correlation between cholesterol and exercise might be entirely confounded by age, which must be accounted for by stratifying the data, shown graphically by dividing the scatter plot into age bands. Moving on, Simpson's paradox. So, this phenomenon, illustrated with Israeli COVID-19 vaccination data, shows how a conclusion over a low efficacy can be reversed when a hidden confounding factor like age, which is strongly associated with severe disease risk, is properly controlled for by analyzing the subgroups. Right now, some real-world applications. So, AI for policy. Studies leveraging Bayesian decision networks, a form of causal modeling, explicitly draw directional conclusions like diversity and longevity. The structure of network was used to conclude that higher diversity mitigates health inequality in the US, with counties having higher diversity being 38% less likely to have a longevity gap. Then preventive care, counties with high quality primary care services have a 43% increase in probability of living beyond 85 years in females. Right. So that's something about the causal inference. And let us see what Anscombe's quartet is again. Right. In the largest context. Okay. So it's basically presented as a stark warning within the context of statistical association, right? So basically, it serves to validate a core instruction in data